This is a video walkthrough for Practice 2D. In 1 through 18, we're going to identify the type of function represented by each equation or graph, choosing from linear, and let's remember what something that's linear looks like. It looks like that. It can typically be written in y equals mx plus b form, or ax plus by is equal to c form. A cubic parent function in equation form looks like that, and its graph looks like that. An absolute value in equation form looks like this, and its graph looks like a V-shape. The square root function in equation form looks like this, and its graph looks like a sideways half of a parabola. And a quadratic function looks like this in parent function form, and its graph looks like a full parabola. And none of these just means it doesn't fit into any of those categories. All right, in number 1, we see a quantity squared, so that's going to be a quadratic function. In 2, we have something that's an ax plus by is equal to c form, so that will be linear. In 3, we have a variable that's cubed, so that will be a cubic. And in number 4, this almost looks linear, except for the fact that the variable is in the denominator of that fraction, so we're dividing by the variable rather than multiplying the variable times something. So this is going to fall into the category of neither. For number 5, I see those absolute value bars, so this is an absolute value function. In number 6, we see the square root symbol, so this is the square root parent function. In number 7, that's the same question as number 2, so it's still linear. For number 8, this is a quadratic function, but we would probably add x squared to both sides and put it in a more standard form for a quadratic function. But the x is squared, so that's quadratic. And number 9, although it looks similar to a quadratic, the x is now in the exponent and the 2 is the base of the exponential expression, so that's a neither. That's actually called an exponential function. We'll study those later in the year. For number 10, this looks like the shape of a cubic function. Number 11 is a line, so that's linear. Number 12 doesn't fit into any of those categories. Number 13 is a V-shape, so that would be an absolute value function. Number 14 has too many bumps to be considered any of the graphs that we've looked at so far. That's neither. We'll study graphs like that in the later part of the course. Number 15 looks like half of that sideways parabola, so that is the square root function, or a transformation of the square root function. Number 16 has a couple of bumps there. That's too many to be a quadratic function, so this is a neither. Number 17 is a parabola shape, so that's a quadratic function. And number 18 is a V-shaped graph, so that would be an absolute value function. For 19 through 29, we're identifying each equation, identifying the parent function, the new origin, and graphing using 5 anchor points if possible. In general, all of our functions will look like this. Y is equal to f of x minus h. I'm just going to use a letter h there, and then plus k. And our new origin in those cases will always be the point h comma k, because the graph will be translated right h and up k if h and k are positive numbers. All right, so in number 19, our parent function is the absolute value function. And let's remember what that looks like. It's a nice little V shape. Our new origin is 5, 0. Now, where did that new origin come from? We can rewrite the equation in the form y equals x minus 5 plus 0, because adding 0 has no effect, so you can explicitly write the plus 0 if you wish. So what that means is, if I graph the new origin at 5, 0, then from that new origin, I can just graph the points on the parent function. So x, absolute value of x, we plug in some negatives, 0, and a couple positives, take their absolute values to get the y values, and then just graph those points as if the new origin were the actual origin. So 2 to the left and 2 up from there, 1 to the left and 1 up, 0 to the left and 0 up, 1 to the right and 1 up, 2 to the right and 2 up. That gives us enough points that we can get a nice accurate graph of this V shape. Please do try to draw it accurately as possible. We can always put additional points in there since both sides are lines. For number 20, this parent function can be rewritten in the form y equals x minus 0 cubed minus 1. We can always subtract 0, and now we have an inside of that cubing. And what that means is the new origin is the point 0, 1. Our parent function is y equals x cubed. Let's remember what that looks like. That's that shape, water slide, if you like that. So I'll graph the new origin, which is the point 0, negative 1. And then from the new origin, we can simply graph, using a table of values, if you wish, y equals x cubed. So we need some negatives, 0, and a couple of positives in order to graph this effectively. Negative 2 cubed is negative 8, negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. Now simply graph those points from the new origin. So from the new origin, 2 left and 8 down. From the new origin, 1 left and 1 down. From the new origin, 0, 0. From the new origin, over to the right 1, up 1. And from the new origin, right 2 and up 8. Now remember, all those points that I was just graphing are measured from the new origin, not from the original origin, if you're using the new origin technique to graph these. Let's take a look at 21. You'll notice that we don't have a parentheses or a grouping indicated here, so I'm going to rewrite this in the form y equals x minus 0 squared plus 3. So our parent function is obviously y equals x squared. Our new origin is the point 0, 3. So I'll graph the point 0, 3. There's the new origin. And we can create a table of values for y equals x squared to graph the points from that new origin. When you are squaring, it's important that you plug in a couple of negative values and 0 and a couple positive values. Square to get the y values. And then graph those points from the new origin. So from the new origin, the first point is negative 2, 4. That's 2 to the left and 4 up from the new origin. 1 to the left and 1 up from the new origin. 0, 0 would be on the new origin. And 1, 1 would be 1 to the right and 1 up from there. And 2 to the right and 4 up from the new origin. That's that nice parabola shape. Connect that with a smooth curve. Moving on to 22. Our parent function here is the square root parent function. Let's remember what that looks like. That's the general shape of it, half of a parabola pointing sideways. And if I rewrite this in the form y is equal to the square root of x plus 2 plus 0, if we stick a plus 0 on the outside, now we can see that the new origin is at -2, 0. So from there, I'm going to graph the new origin, -2, 0. And then I'm just going to use a table to graph the parent function from the new origin. And for the x values, we need to choose carefully. The smallest value that you can take the square root of is 0 and get a real result. So the square root of 0 is 0. We can take the square root of 1 and get a whole number. The result is 1. We can take the square root of 4 and get a whole number. The result is 2. And we can take the square root of 9 as well and get a whole number. The result is 3. From the new origin, graph the point 0, 0. So 0, 0 is on the new origin. 1, 1 is 1 to the right and 1 up. 4, 2 is 4 to the right of the new origin and 2 up. 9, 3 is 9 to the right of the new origin and 3 up. And now we have that nice square root shape there. For 23, our parent function is the cubic because we see the exponent of 3. The new origin is -4, 1. And let's graph that new origin, -4, 1. And if we want to, we can graph the parent function directly from that new origin. When I cube, it's important, if we want to see the shape accurately, that I cube a couple of negatives, 0, and a couple of positives. -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So from the new origin, go 2 to the left and 8 down. From the new origin, go 1 to the left and 1 down. 0, 0 would be right on the new origin. 1, 1 would be 1 to the right and 1 up from the new origin. And 2, 8 would be 2 to the right and up 8 from the new origin. It's important, again, that you count from the new origin to graph each of those points. For number 24, we have a quadratic function again. Our parent function is y equals x squared. Remember, that's going to look like that parabola shape. And our new origin is at the point 2, -5. So there's our new origin. And to graph points from there, we're just going to graph the original parent function, which is y equals x squared. When we square, we want to consider a couple of negatives, 0 and a couple of positive values to square. Let's square them. And then from the new origin, -2, 4 means go 2 to the left and 4 up from the new origin. -1, 1 means go 1 to the left and 1 up from the new origin. 0, 0 is on the new origin. 1, 1 is 1 to the right and 1 up from the new origin. And 2, 4 is 2 to the right and 4 up from the new origin. And I want to connect with a nice smooth curve to form that parabola shape. And there's our entire graph. Let's take a look at 25. For 25, our parent function is y equals the square root of x, which has that nice sideways half parabola shape. And the new origin is at the point -4, -3. And -4, -3 right there. To graph the points from the new origin, just create a table of values for y equals the square root of x. So when we're taking a square root, the best numbers to plug in to get a nice graph are 0, 1, 4, and 9, because we can take those square roots of those numbers and get a whole number. The square root of 0 is 0, the square root of 1 is 1, The square root of 4 is 2, and the square root of 9 is 3. 0, 0's on the new origin. 1, 1 is 1 to the right and 1 up from the new origin. 4, 2 is 4 to the right and 2 up from the new origin. And 9, 3 is 9 to the right and 3 up from the new origin. That gives us that nice parabola shape, just a half of one sitting sideways. For number 26, the parent function is y equals the absolute value of x. The new origin is the point 3, 2, and I'll graph that new origin point. So 3, 2 right there. And to graph the parent function from there, we can, if you wish, create a table of values. Maybe once you've done this a few times, you won't actually have to create the table of values. You may do this in your head. For absolute values, we need to pick a couple of negatives, 0, a couple of positives to take the absolute value of. Let's take their absolute values and then graph those points from the new origin. So from the new origin, negative 2, 2 is 2 to the left and 2 up from the new origin. Negative 1, 1 is 1 to the left, 1 up from the new origin. 0, 0's on the new origin. 1, 1's on 1 to the right and 1 up. And 2, 2 is 2 to the right and 2 up from the new origin. That gives us our nice characteristic V shape for an absolute value function. And for number 27, we have a quadratic function. So our parent function is y equals x squared. The new origin is at the point negative 1, negative 3. So I'll graph the new origin, negative 1, negative 3. And then to graph the rest of the function, use a table of values for the parent function, y equals x squared, and then graph those points from the new origin. When we square, we need to consider x values that are negative, a couple of those, and 0, and a couple of positive values. Let's square to get the result, and then plot those points from the new origin. Negative 2, 4 is 2 to the left and 4 up from the new origin. Negative 1 is 1 to the left, 1 up from the new origin. 0, 0's on the new origin. 1, 1 is 1 to the right and 1 up from the new origin. 2, 4 is 2 to the right and 4 up from the new origin. There are 5 points that are plotted explicitly, and connect for a nice smooth curve to plot our parabola. For number 28, the parent function is y equals the square root of x, which has that characteristic half of a parabola pointing sideways shape. The new origin is at the point 1, 2. So let's graph the point 1, 2. Right there is the new origin. Then in order to graph from there, I'm going to use the parent function for the square root of x. So when we're taking a square root, the numbers that we're going to plug in are a little different. There are the numbers that will give us a whole number square root. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. So 0, 0 will be graphed on the new origin. 1, 1 is 1 to the right and 1 up from the new origin. 4, 2 is 4 to the right and 2 up from the new origin. And 9, 3 is 9 to the right and 3 up from the new origin. Now that we have all those points explicitly plotted, I can connect and put an arrow on the end of the graph. Notice this graph stops at one end. For number 29, the last, our parent function is y equals x cubed. The new origin is the point 3, negative 1. Remember, y equals x cubed should look like that. And I'll graph the new origin point, which is 3, negative 1. There's the new origin. To graph the rest of the function, we can create a table of values for y equals x cubed. When you are cubing, we need to consider a couple negative values, 0 and a couple positive values. -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So now we can graph these points from the new origin. -2, -8 is 2 to the left and 8 down from the new origin. -1 is 1 to the left and 1 down from the new origin. 0, 0 is on the new origin. 1, 1 is 1 to the right and 1 up from the new origin. 2, 8 is 2 to the right and 8 up from the new origin. Again, it's important that we count these points from the new origin. Connect for that characteristic cubic shaped curve, and we are done.